Welcome to this video lecture on code generation and code optimization. In this video lecture, we'll talk about principal source of optimization and peephole optimization. To start with, first of all, we'll see what is principal source of optimization and when to optimize your code. So optimization of the code is often performed at the last stage of the compiler. Since it reduces the readability and add code that is to increase the performance. So whenever we optimize a code, definitely it will increase the efficiency of the overall program. So why we need to optimize the code? So optimizing an algorithm is beyond the scope of code optimization phase. So the program is optimized and it may involve reducing the size of the code. So whenever we optimize a code, it helps us to reduce the space consumed and increase the speed of execution or compilation. So many analysis dataset involves a lot of time. So we make use of softwares like Tableau or Power BI for data analysis. So manually performing the optimization is also tedious and it is better to done with the code optimizer. An optimized code often provides reusability. So this is why we need to optimize the code. Now, and we have different types of code optimization also. So one is mission independent optimization and mission dependent optimization. In the independent optimization, uh, the intermediate code uh, will get better to make the uh, better target code as the output. So here the intermediate code transform does not involve any CPU registers or absolute memory location. So that is why we call this as an mission independent optimization, which means this optimized code can able to run at any kind of platforms. Similarly, when it comes for mission dependent optimization, so here also it improves the target code according to the target mission architecture. So here it depends on the mission architecture, and here it involves CPU registers and may involve absolute memory references or locations also. So and it takes many advantages of the memory also. So we here the usage of memory will be more. So there are two types of, and these are the two different types of code optimizations that can be performed. Now we'll see into the principal source of optimization. So here e- an optimization can be performed by looking. If we optimize a code only upon looking the statements in a basic block, we call that as a global source of transformation. Otherwise, it is called as the local. So now we'll see about the principal source of optimization. Here, if an optimization can be performed by looking only at the statements in the basic block, we call that as a local transformation. Otherwise, we call that as a global transformation. So many transformations can be performed at both local and global levels, but we prefer the local transformation. So here we have two different types. One is the function preserving transformation. So what is meant by function means without changing the flow or without changing the functionality of the original program, we will optimize the code. Right? So these are the different examples. We have four different examples here that will do the function preserving transformation. One is common sub-expression elimination, copy propagation, dead code elimination, and constant folding. The other source of optimization is the loop optimization. As we all know that whenever there is a code, this loop plays a major role, which means the program spends more time on the loops. So optimizing the loop is very, very important. So for that, what we will use is that code motion or induction variable elimination or reduction in strength. So we'll see each and everything with an example. To start with, we'll go with the function preserving transformation. So first one, that is the common sub-expression elimination. So here an occurrence of an expression E is called common sub-expression when means if E was previously computed and the values of the variable in E have not changed since the previous completion. So we can avoid recomputing the expression if we can use the previously computed expression. So in this example, here t equal to 4 into I. After that we are performing t2 equal to a of t1. Again if you check here, we are performing an t3 equal to 4 into j. And in the next step, if you check here, t4 equal to 4 into I. But the 4 into I is already been performed and it is stored in the value t1. So we don't need of this. We can reuse it. Okay. So here that is what they said, we can avoid recomputing the expression, so we can make use of the previously computed value. So this can be rewritten as, so instead of having, this is where we will be using again 4 into I. So what we can do is that here instead of this t4 we can have t1. This is what we call it as a common sub expression elimination. Next one, copy propagation. So here, if there is any assignment of form f is equal to j, called copy statements or copies for short. So the idea behind the copy propagation transformation is to use g for f. This is the meaning for it. Whenever possible, wherever it is possible, after copy statement f is equal to g, here the copy propagation means use of one variable instead of other. Here using g instead of f. That is what we say. So this may not this may not appear to be an improvement, but we shall use it, or we shall see it as to eliminate x. For example, here x equal to pi, and then in this expression a equal to x star r star r. So what is the need for this? This is not needed and it is not meaningful also. So this what we call it as the copy propagation. So instead of pi we are using x, but directly we can write it as a is equal to pi star r star r. This is what we call it as a copy propagation. Next one is the dead code elimination, right? In dead code elimination is one of the most important optimization technique, so which is used to remove the code that will never be executed or whose results are never been used. A variable is live at a point in a program if its value might be used in some part of the program that comes after this particular code or particular point. So when we say when a variable is dead at a point, if the variable is no longer or the value is no longer used anywhere after the point in a program. So what is the purpose of using this dead variable in the rest of the code? So we can remove that. That we call it as the dead code elimination. When you take this example which has been given here, here I is equal to 0. So if you check in this if statement, if 0 equal to 0, condition is true, right? So here 0 equal to 0, right? So a equal to x plus I. See here, this particular part is not there is no need to use of it. Why? Because the code a or x is not being used in any of the further rest of the program, so this is not needed. So and we consider this as a dead code, so we can eliminate this and we can have only I is equal to 0. Next one is the constant folding. So here constant folding means deducing at compile time that the value of an expression is constant and using the constant instead we known it as constant folding. See for example, if a is equal to 3.14 divided by 2, so what we can do is that this expression can be replaced with a equal to 1.5. So you just think of it, what is the need for division here? So we can reduce this operation, right? So wherever it is needed we need to reduce, so that what we call this two, if we perform the division of these two things it will give one constant, and we know the exact value of it. So instead of having the division operation to be performed extra, so what we can do, we can replace that with the exact constant value, right? Next one, constant propagation. So what does this constant propagation means? For example, if pi is equal to 3.14 and r is equal to 5, right? So here the constants replaces the variable, right? So area equal to pi star 5. So instead of having this, if you know that this pi or r will be used once, we can directly substitute the value or the constant directly instead of using pi star r star r. 3.1455. So if this is what we call it as the constant propagation. Instead of propagating the constant throughout the expression, constants replaces the variable, right? So we know that pi and rsu will be used only in this particular expression, means then there is no need for declaring a variable, so which will take a space. So what we can do, directly have that value in the expression itself. So this is a small example here. This is a flow graph which we have taken here, and we have around 6 blocks were present. When we take the last block here, B5, so here we can apply what we have seen before, that is the common sub-expression elimination. T6 is equal to 4 star I. Again we are performing 4 star I and storing that in T7, so which is not needed. Similar to it, we perform 4 star J here, and then again 4 star J is also being performed here, which is also not needed. So we can re remove the common sub-expression, that is the common sub-expression elimination can be performed in block B5. So upon changing this, we will be getting the blocks like this. So here when you see this entire flow graph is being reduced like this. So this is what we call it as the code optimization. Even then we can also reduce further. See, this is for B5, but when you take this entire flow graph, in block B2 itself we have computed 4 star I, and in block B3 is equal to we have in block B3 itself we have computed 4 star J. So instead of having the separate thing in block B5, we can make use of this temporary variable T2 and T4 wherever we need 4 star I and 4 star J. Right? So this is what is the optimization, where we will be using the optimization here. Right? So this is the given actually constructed flow graph from the 3 address code, but this particular flow graph is the optimized one. I think you might understand what is the need for code optimization. Next one, as I said you before, this loop plays a major role in the entire program. So here we'll see. So whenever in loops alone, especially inside the loop, the program tends to spend a more amount of time. So the runtime of the program may be improved if the number of instructions in the inner loop is being reduced, even if we increase the amount of code outside the loop. So for that, first technique is code motion. So an important modification that increases the amount of code in a loop is code motion. So here in this transformation, it takes an expression that yields the same result independent of number of times the loop is being executed. That is, we call that as a loop invariant statement, and place that expression before the loop. When you consider this example, this is the loop, and here we have one statement called x is equal to y plus 3, and after that a of I is equal to 6 into I. Here this particular statement is making use of this loop variable I, but so then this particular expression value will be changed whenever the loop is being iterated. But when you check with this statement, this x and y value will be constant, which means this entire expression value will be the same throughout the loop. So why should we have this inside this loop? So we may have that particular statement outside. So then this code will be executed, or this particular loop will be executed. Execution time will be reduced. So this is what we call it as the code motion, moving of your code which is independent or loop invariant to outside the loop. Next one is the induction variable elimination. A variable x is said to be an induction variable if there is a positive or negative constancy such that each time x is assigned, its value will be increased by c. I will see one example. So induction variable can be computed with single increment, or that might be an addition or subtraction per loop iteration, right? So induction variable means there is a positive or negative constant which will increase each time it will increase to 1 or decrease to 1, right? So reduction, together we'll see one example, and then but before that we'll see this also, reduction in strength. The transformation of replacing an expensive operation with a cheaper one, we call it as an strength reduction, right? So this kind of replacement will speed up your object code. That is the generation of the final bytecode or object or target code. So here t equal to 4 into I. Yeah, we can replace this with t equal to 12 plus 4. So we'll see that example. So instead of performing the multiplication operation which will take more time, so we can perform repetitive addition which is very simple and it takes less amount of time. Here we have an example here. See T4 is equal to 4 into J, right? So this particular thing, when you take this block, we are not using or we can replace this one. Okay. So what we can do is that first step we do code motion. We are moving this out of it. Okay. So 4 into J. Initially whatever the J value will have that. For example, if your J value is 5 here, okay, we'll have the J value as 5 or N value as 5. So J equal to N means J will be 5 here. When it enters inside this particular block, J equal to J minus 1. So which means J value will be 4. So T4 is equal to 4 into 4 which will be 16. Right? Now, and in the next iteration if you check, again we will decrement the J value. So which means it will be 4. Now it will be 3. So which means 4 into 3, 12. Again in the next iteration it will be 2. So 4 into 2 it is 4, 8. So how we are reducing, please check here. We are now replacing this multiplication operation here. Please be careful. Carefully watch this. So here we have just moved this code out of it, right? So we are fixing T4 will be a 4 into J. That is, for example, if my N value is equal to 5 means J will be 5. Okay. So T4 is equal to 4 into 5 which is 20. We are fixing this T4 value, right? Now, if you enter inside this loop, J equal to J minus 1, which means J value now will be 4. T4 is equal to, what is T4? 20. 20 minus 4 we can have, right? And then now this T4 value will be replaced as 20 minus 4 which is 16. Okay. So then again if you go back here, J equal to J minus 1, just decrement. So here this particular J value is now used to or it will say how many times this particular loop will be running instead of performing the multiplication operation. See, when you take this particular block, at each time when you see the T4 value, it will be starting with 20, then 16, then it will be 12, then it will be 8, then it will be 4, then it will be 1 or 0. So each time it is getting incremented to 4. That's it. Very simple. So instead of performing this multiplication operation, we are replacing that with subtraction. The time will be reduced, and similar to it, we are moving this T4 is equal to 4 into J out of the loop also. So here we are performing code motion. So definitely it will optimize my entire code. This is what we call it as an induction variable elimination, what we have done before, the constant increase or decrease. And here this is the reduction in strength. Instead of performing the multiplication, we are doing the subtraction operation here, right? So this is what is the principal source of optimization is about. So next one, which is one of the most important optimization technique that we will use, is the peephole. From the name itself, peephole means a small moving window on the target program. So here, the peephole optimization, what we will do is that replace a short sequence of target instruction with the shorter or faster sequence. We will do only the short replacement of my entire program. Redundant instruction elimination, unreachable code elimination, flow of control optimization, algebraic simplification and use of machine idioms. First one we'll see about redundant load and store elimination. So here this will be an initialized code here. Y is equal to x plus j and x equal to y, z equal to y, w equal to z into 3. So here we can eliminate, we can reduce the redundancy in the code. Redundancy is eliminated here. We'll see what is the redundancy here. This is what we call it as a redundancy here. Y equal to x plus 5 is okay. So what is the need for this thing? Instead of having this thing, we can directly say w equal to y into 3, assigning y to I, again I to z, then using z here. This particular thing is not needed, right? So here w equal to y into 3, we can do it. So here we are removing two redundant variable I and j here. So here also the same example we have seen in the previous video lectures. Move r0 comma x and again moving r0 back to x, which is not needed. This is the another example for a redundancy. This is we call it as a redundant store and load elimination. Next one, unreachable code, right? It's a technique which is used to remove the code that never be executed or often due to incorrect or redundant logic. So if you check here, a equal to 5, go to L. Go to L means it will go here. So L is equal to C into A plus I and D equal to C into D. If you check here, this code will never be executed. So this can be eliminated. Similar to it, if x is greater than 0, go to L2, which means it will go here. Think of that always your x value. X is positive. What happens? Always it will be true, right? So by default L2 will be executed. So what is the use of this y equal to 20? Just remove that. So when you take this particular function statement here, in the function we have in c equal to a plus b. After that what we have done? Return c. Return c means we know that whenever the inside a function if there is a return statement, that is the end of your function. Then what is the use of printing c value here? Definitely when I give return C, it will return back to the calling area or the caller function, right? So then this printf is not needed or it will never be executed. So we can eliminate this, right? So this is what we call it as an unreachable code elimination. The next one is the flow control optimization. So here we have three things: eliminating jumps to unconditional jumps, then simplifying conditional jumps and removing redundant jumps. We'll see an example here. So eliminating jumps to unconditional jumps. Here we have go to L1 and then we have L1 go to L2, L2 equal to L2, that is A equal to B plus C. What is the need for this jump here? Instead of having this, we can directly say go to L2, go to L1. L1 is having again the jump to L2. So what is the need for this? So we can directly write it as go to L2, L2 equal to A equal to L plus B plus C. Okay, this is the unconditional jumps and eliminating those jumps to unconditional jumps. Okay, then simplifying the jump conditions. See here, if x is less than y, go to L1. So what we have in L1, a equal to b plus c. Okay, so then L2 will be executed. So what we can do is that directly we can say if x is greater than or equal to y. Very simple. If x is greater than or equal to y, go to L2. Otherwise, what it will do? It will perform a equal to b plus c. So what is the need for this? We are trying to remove this particular go to here. Here we have two jumps, but we are reducing this to one jump here. That is the simplifying conditional jumps. Then removing the redundant jumps. This is also important. Here if x is less than y, go to L1. Okay. So this is a redundant jump. Again, if this becomes true, what if this becomes true, it will go to L1. Otherwise, it will go to L2. Instead of having this go to L2, we can even have a statement here itself, right? Yes. So instruction 3 go to L2 is a redundant one. So because the control to L2 directly or executed or it will be directly going to L2 after L1. So what is the use of it? So we can eliminate that also, right? This is flow control transformation. And the next one is the constant folding. So here the code that can be simplified by the user itself. Here the simplification is to be done at the runtime is replaced with simplified code to avoid additional computation. Simple. The same thing we have already discussed. X is equal to 2 into 3. Instead of having the multiplication operation to be performed here, we can replace this with x equal to 6. So strength reduction we know. So instead of performing the big operations like multiplication, we can reduce that to addition or subtraction like that. See here, x equal to, y equal to x into star, which can be optimized as y equal to x plus x or y is x left shift of 1. So we may know that left shift, it will perform if left shift of 1 means if you do the same thing x into 2, the results will be the same. Similar to it, if you perform x right shift right shift of 1, it is division. So then here x is equal to x divided by 2 can be replaced with x is right shift of 1. Shift operation will take less time when compared to addition or subdivision. So shift operation, then we'll have the first one. Less time will be consumed for shift operation. After that, for arithmetic operations like addition, subtraction, then it consumes more time for multiplication and division. So wherever it is possible, we can reduce that code here. So null sequence or next one will be the algebraic expression. So here useless operations are deleted. So a equal to a plus 0, a equal to a into 1, a equal to a divided by 0, a equal to a. What is the need for this? So all these things we are assigning back to a. But the last value alone will be preserved. What is the need for this? So this is the useless operations that we need to eliminate. So and then use of the mission idioms. So replacing the arithmetic sequence with mission specific instructions like x equal to x plus 2 can be replaced as x equal to left shift of 1. So it is efficient to do shifting instead of performing or replacing that with multiplication. And then increment decrement idioms. X is equal to c plus 1. Instead of having this, we can use inc x. Very simple. This is also the same. X equal to x plus 1, not c. X equal to x plus 1. So we can here replace it with a single mission instruction. So loop optimization idioms means for here, this is the loop. So this can we can rewrite this with an small instruction memory like AVX or SSC is used for parallel processing. So for this kind of array or parallel processing, we can make use of it. So this is the use of the mission idioms. Right? So these are the optimization techniques what we have discussed. So in this video, we have discussed about the principal source of optimization and one most important optimization technique, that is the peephole optimization technique. Thank you.